So let's have the solution to example 15. So knowing that the tension in cable AC is 1,260 newtons, determine letter A, the angle between AC and the boom AB, and the projection on AB of the force exerted by the cable AC at point A. Then letter C, the moment of this force about point B. So first, I'll present the trigonometric approach. So let's use trigonometry in analyzing this problem because this is just about triangles. So we have triangle ABC. We can compute the length of each side of this triangle. Then by cosine law, we can solve for the angle between AC and AB. So we have distance AC equals square root of 2.4 because x is 2.4. Y is zero point 0.8 because this is 2.4 above the horizontal plane. A is only 1.8 above the horizontal plane. So delta y is 2.6 minus 1.8. So we have there quantity square plus delta z is 1.2. So move to the left 2.4, move upward by zero point 0.8, and move forward by 1.2. These are the components of distance AC. So distance AC therefore is 2.8 meters. Next, distance BC. It is the square root of 2.6 square plus 1.2 square. So distance BC is 2.8636. Then distance AB is square root of 2.4 square plus 1.8 square. So distance AB is 3 meters. Again, distance BC is square root of, there's no delta x, so 0 square. Delta y is 2.6, so 2.6 square plus 1.2 square. That's why you get 2.8636. Now that we have defined the sides of this triangle, we apply cosine law to solve for this angle theta. So opposite of this angle theta is BC. So BC square equals 2.8 square plus 3 square minus 2 times 2.8 times 3 cosine of theta. Remember cosine law. So solving for theta, theta is 59.05 degrees. Next is we compute the component of the force, which is 1,260, which serves as the hypotenuse, and its projection upon AB or onto AB is 1,260 times cosine of theta. So to show that, so we have 1,260, this is the right triangle, and that angle is theta. Then therefore this component or the projection of 1,260 newtons along AB is 1,260 cosine of theta. Where cosine theta is FAB, we will call the projection of the force onto AB as FAB. So cosine theta is FAB over hypotenuse 1,260. So cosine of 59.05 degrees equals FAB over 1,260. So FAB is hypotenuse times cosine theta. 1,260 cosine of 59.05 is 648 newtons. Then the moment of this force about B, we can compute the scalar value, just the magnitude. But in vector form, we will use the vector form later. So imagine this is the perpendicular distance of the force from point B, the moment center. So it is equal to 1 to 60 times this perpendicular distance because this is again a right triangle with hypotenuse equal to AB. Then and AB is equal to 3. So therefore, the moment is 1 to 60 times this perpendicular distance is AB, distance AB, sine of theta. Then substitute, distance AB is 3, theta is 59.05 degrees. So the magnitude of the moment of the force about point B is 3,421.8 Newton meter. But we want to compute the components. So let's resolve 1,260 Newton force into its components to compute the components of the moments about point B, so that we can write the result in vector form. So MBX is, remember, there are components of the force, Fx, which is to the left, and because that component is equal to 1260 times supposedly negative 2.4 over 2.8, then you'll get moment about x-axis. So that is ignored because it is parallel to the x-axis. The y component is upward, and that upward component is zero point 0.8, because this is zero point 0.8 divided by 2.8 times 1 to 60. Remember the component of the force, it is equal to the magnitude of the force, component of distance divided by distance. The y component of distance is zero point 0.8, the distance is 2.8. So, however, that vertical component of force, if you extend it, will cross the x-axis. So there is no moment of that force about the x-axis. Finally, the z component is 1260 times component of distance, z component of distance 1.2 divided by 2.8. That would be 540 forward. And its moment about the x-axis, if we apply right thumb rule, is positive. So try to use your right thumb, then position your right thumb towards the positive x-axis. Then this component, forward component of the force, which is 540 newtons, will create positive moment about the x-axis. So 540, the moment arm is 1.8, is 972 Newton meter. Then MBY is equal to, that's the force, these are the components, 1080 leftward, 360 upward, and 540 forward. So MBY is equal to, so the x component passes to the y-axis, so 0 moment. Then the z component, ignore the y component because it is parallel to y. The z component, applying right thumb rule, would be negative. So it is equal to negative 540, moment arm is 2.4, or distance with respect to the y-axis is 2.4. So it is negative 540 times 2.4. So negative 1296 Newton meter. And finally, moment about z, applying the right thumb rule, the x component of the force, which is leftward, produces positive moment about the z-axis. The y component, which is upward, also produces positive moment about the z-axis, while the z component is parallel to z, so that is ignored. So only fx and fy are considered, and both produce counterclockwise moment about the z-axis, or produce positive moment about the z-axis. So the horizontal component is 1080, the x component is 1080, and the moment arm is 1.8 plus Fy, which is 360, and the moment arm or distance from the z-axis is 2.4. So MBC is 1080 times 1.8 plus 360 times 2.4. So negative 1296 Newton meter. In vector form, moment about B is equal to 972I minus 1296J plus negative, positive 2808 K Newton meter. So that's the moment about Z. So moment about BC is 2800. Now, if you solve for the magnitude of this moment, square root of 972 square plus 1296 square plus 2808 square, it will give us this value 3421.8 Newton meter. Now, let's proceed to the vector approach by computing data. So we have to obtain the dot product between AC and AB. AC dot AB, by definition, is equal to magnitude of AC, magnitude of AB times cosine of the angle between them. AC in vector form, so we consider AC in vector form. it is equal to negative 2.4i, positive 0.8j, then positive 1.2k. So that's it. While AB is A to B. So go left, then down. So negative 2.4i, negative 1.8j. Then remember that the dot product between two vectors is simply the sum of the product of corresponding components. So it is negative 2.4, negative 2.4, or negative 2.4 square plus zero point 0.8 times negative 1.8. Then there's no z component, 0. Equals AC, which is 2.8, AB, which is 3 times cosine of the angle. Solving for the angle theta, it is equal to 59.05 degrees, which is the same as this. Then for the component of the force along AB, it is equal to force 1 to 60. So we have to obtain the dot product between the force. Let's write the force in vector form and AB. So this is already the vector form of the force. So we simply dot it with AB. So F dot AB equals magnitude of the force, which is 1 to 60, times AB, which is 3, cosine of theta, which is 59.05 degrees. So by definition, this is sum of product of corresponding components. So negative 1080 times negative 2.4 plus 360 times negative 1.8. So that's it. Then equals 1 to 60 times 3 cosine of 59.05. So the component of the force 1 to 60 along AB is, it is equal to F times cosine of theta. So F cosine theta, which is found from this equation here. So F cosine theta, which is this magnitude here, is equal to F dot AB divided by magnitude of AB, because F cosine theta is the one that is we want to find or compute the component of F in the direction of AB, which is this. So negative 1080 times negative 2.4 plus 360 times negative 1.8, which is that. There's no z component, divided by AB, which is the magnitude of AB is 3. So solving for FAB cosine theta, or FAB, is equal to 648 newtons. Then finally, for moment about point B in vector form, so this is the moment center. A is the point on the line of action of the force, or it may also be C, but I'll only present RBA cross F. It is also equal to RBC cross F to compute the moment about the vector form. So it is RBA cross F or RBC cross F. I will leave this second definition for moment of B about F to verify that the answers will be the same. So RBA, so B to A, since this is now B to A, from the point or moment center to point on the line of action of the force, so it is rightward and upward. So it is now the opposite of this vector here. So it is 2.4, positive 2.4, positive 1.80 in matrix form. So components of RBA, 2.4, 1.80, components of the force, negative 1080, 360, and 540. Then components of the unit vectors, or these are the unit vectors. Then copy the first two columns, then apply basket method or Cramer's rule. So let's begin with I. 540 times 1.8i positive, which is 540 times 1.8, which is this, right? Then minus 360 times 0, so minus 0, so that's why there's no more term here. So it is just 540 times 1.8, so it is equal to 972i. Then for j, it is 0, 0 times, or negative 1080 times 0. Then minus 540 times 2.4j. So there should be negative 540 times 2.4, which is this, heavy one. So negative 1296J. Then for K, 360 times 2.4, which is this, and minus negative 1080 times 1.8. So minus of negative 1080 times 1.8 is positive 1080 times 0.8, which is this. So therefore, the result is the same, 2808K. So in vector form, that's the result. It's the same as this.